If it goes under a 1, it'll probably do a single swap. So cost will be 2. How often? Well, you have your 1s, you have your 2s, and you have half the 3s. So 2 parts 1s, 2 parts 2s, 1 part 3s. Total of 5 different parts. How many parts does a 2 not move under? 3. Because you're going to have the 3s and the 2s and the 2s. So 60% of the time, that 2 will hit a 2 or a 3. So 60% of the time, 0.6 is going to be one comparison and you're done. And 40% is going to be 2 comparisons. Okay. How about a 3? What is the probability that a 3 goes in and stays where it was put? Well, remember what we had. 2 parts 1, 2 parts 2, 1 part 3. It's a total of 5 parts. So the probability that a 3 comes in and hits another 3 is roughly 20%. So 20% chance that it goes under a 3 is going to do what? It's going to stay. 80% of the time it's going to hit a 2 or a 1, it's going to go up. So it's going to require 12. When it goes up, it's going to go up from the lowest level to one level higher. And what's it going to do next? What's the probability that it's going to do? Pretty much going to stay. Because it's going to move to the next level. And the next level, remember what's on the next level? It starts with 3s, 4s, and 5s. Which means it's really going to be some 3s and the rest 4s. And then the 4s will continue for a while. And then all the 5s will take over. How deep in the tree are the 5s? Well, the 5s are 20%. 20%. Let's think about it. What part of a binary full tree is at the bottom? 50%. Let's go to the next level. What part is that? 25%. Add them together. 75. How about the next level? 12 and a half, right? So we have 50 plus 25 is 75 plus 12, 87. 87 is very close to 8. So that means in the top 17 levels, we're going to have only what? Only priority what? 5. Only priority 5. That's the expectation. The expectation is that after we take out the first 3 levels, it's going to be all 5s. Why? Because it's a binary tree, and it's just how it works. You have 50%, 25%, 12.5%, 6.25%, 3 and an 8. That's just how it works. So that means if a priority 5 element comes in, what is the worst number of comparisons we can expect? Because it's not going to, once it meets a 5, it's done. It's not going anywhere. So what's the worst expectation for a 5 in terms of number of swaps?
3.
It's about 3. And if you said 4, I'd say, okay. You know, I mean, look, we're not going to argue about 3 or 4. So in a sense, would you agree under this scenario that if we have a priority queue of 5 priorities, which are all equally likely, that we could make the argument that the insertion into the priority queue is theta 1? Because in the worst case, it's 3. Let's call them all 3. Then 3 is pretty much a constant. So therefore, we are talking about a theta 1 insertion complexity. What about the dequeuing complexity? Well, the dequeuing complexity actually is more expensive. Why? Let's see what happens in a dequeue. On a dequeue, what we're going to have, we're going to remove the top element from the root, right? We're going to exchange it with the last element in the array, put it into the root. That element has, what's the probability that element will be priority 1? 40%. And probability that it's going to be a 2? 40%. And the probability is gonna be 3? 20%. That's just the crazy numbers I made up. So now we can count the expectation of the number of swap. Now you understand that if a 1 or a 2 or a 3 go up, which is pretty much a guarantee that one of those is going to go up in exchange with the root, it will swap down LGN minus 3, roughly, right? Because it's got to get past all the what? Once we exchange that low element, put it here, it's got to swap down past all the what? Priority. How many levels are our 5s? 17. So if that 1, 2, or 3 goes up here, it's got to go past all of them, it's got to do 17. So therefore, we'll say that theta will be what, approximately? Approximately what? What kind of theta would you assign it? Well, so a DQ from the priority queue requires removing the root. So when we remove the root, what we really do, remove the root, put the nth element into the root, and then swap it down exponentially. What's the cost of that swap down? These are easy questions. You know that. You know the answer. Give me answers to hard questions, right? If I have a million elements, take the top element out, I take the last element, last child here, put it here. It's got to swap down those 17 levels. Got to swap down, right? And 17 is very close to 20. Just like 3 was very close to 1. 17 is very close to 20, so it becomes closer to what? Right.
Log n.
Now, let's see if our logic makes sense if we scale this thing up. Let's increase the size of the priority queue from 1 million to 1 billion elements, shall we? 1 billion. It's crazy. How many levels do you think the top priorities 1, 2, 3 will take? So I have 1 billion, not 1 million, but 1 billion elements. Same probabilities, 1 through 5, equally likely. That means that 20% of 1 billion, or 200 million, are going to be at the bottom level. How big is the bottom level? How many elements in the bottom level? 500 million. So 200 million, priority 1, 200 million, priority 2, and 1 million, 50% of priority 3. Notice that our ratios haven't changed a bit. So that means that priority 1, 2, and 3 will only be residing in what area? Levels, bottom level, bottom 2 levels. Just like before. So that tells us that the insert operation will be the same as we had before. It's still going to be theta 1, which is going to be about three comparisons. But how about our DQ operation? Now we have to swap down, instead of 20 levels, we might have to swap down 27 levels, because we have 1 billion is 2 to the 30th power. So therefore we are ensuring that we are understanding that we're basically still talking about theta log n for the DQ and theta 1 for the NQ. Even if I made 1 trillion, my NQ would still be linear complexity, constant time. And my DQ would be log n of 1 trillion. Get the idea? Interesting. So for a test question, or for a homework question, I love looking at the priority queue with probabilities. And, for example, I could do something like, I could play around with the percentages. What percentage are going to be priority 1, 2, 3, 4, 5, et cetera, et cetera. But it's that type of thinking. So I want you just thinking about populating the tree with those probabilities. And that's what we did. That's what we did. If we only had two probabilities equally likely, two probabilities equally likely. Where would the bottom level, if we only had priority one, priority two, where would priority one go? They'll all be at the bottom. Priority two, every other level. Because 50% is the bottom level, and all the other levels amount to the other 50%. So if we only had two priorities, everything by and large would be priority one at the bottom level, which means the insertion of the one would have theta of one, still very, very similar analysis. Okay, so anyway, so that's it for today.